Assalamualaikum and good day to all of you. So today I will discuss on chapter 4, magnetic circuit. So these are the content for part A, and then these are the content for part B. So today I will discuss on part A. Okay, the learning outcome for this chapter is represent magnetic fields using Faraday's flux concept, describe magnetic field quantitatively in terms of flux and flux density, explain what magnetic circuits are and why they are used, determine magnetic field intensity, or we call it B, from a BH curve, solve series and parallel magnetic circuits. So the nature of magnetic field. What is magnetism? Magnetism refers to the force that acts between magnets and magnetic materials. So the region where the force is existed is called magnetic field. Faraday's flux concept helps us visualize this field. And then magnetic field can be shown as line in space, or we call it flux line. So this line we refer to flux line. Okay, symbol of magnetic flux is phi. So the line we call phi. The field is strongest at the poles. So you can see at the poles here, the gap of your phi or your flux is shorter than this one. And then direction of flux line is from north to south externally. Internally, so your flux line will directed from south to north, and then the flux line never cross each other. Okay, characteristic of lines of magnetic flux. So if you place a compass here, you can see that the direction of your needle will direct into this orientation. So where it will directed from north to south. So each line of magnetic flux form a closed loop. Line of magnetic flux never intersect, and then flux line of opposite pole will attract one another. So you have two magnetic material or two magnet bar. So you place as in this direction, south and north here. So it will attract each other. Okay, so if you place your magnet of same pole, so same pole here, south and south, so your flux line will repel one another. So what is ferromagnetic material? So ferromagnetic material refer to the material that are attracted by magnets such iron, nickel, cobalt and others. So this material we call ferromagnetic material. And the non-magnetic material is like plastic, wood and glass. So if you place ferromagnetic material here, so here we use soft iron, you can see that the flux line from non-uniform so will be in uniform path if you place ferromagnetic material, because it provides easy path for magnetic flux. So if you place non-magnetic material, it will give you no effect to your flux line. The source of magnetic field. So what is source of magnetic field? So it is electric charge in motion. So for example, you have one rod, a conductor rod. Okay, so and then to get the similar field as the bar magnet, you have to supply current. And then okay, and then the electromagnetism. So what is electromagnetism? Generally, you have two types of magnet. So you have permanent magnet, where is your magnet bar, and then electromagnet. So what is electromagnet? So electromagnet is you supply a current into a conductor or ferromagnetic material. So when you supply the current, it will create magnetic field that concentrate about the conductor. Okay, and it will produce a flux. So the direction of the flux is determined by using right-hand rule. So the video explaining the basic principle of electromagnetism. So please watch video 1 in ULearn. So if the conductor is wound into a coil, the field is of its individual turns combined, producing a resultant field. So you have solenoid. So this one we call solenoid. So you give or supply the current into the solenoid, so it will produce magnetic field. Okay, so in magnetic circuit analysis, normally we neglect the leakage flux. Okay, so how to determine the poles? The explanation how to determine the poles is in video 2. So please watch the video. Okay, and then flux and flux density. So magnetic flux is represented by the symbol of Phi. The unit of the flux we call Weber, WB, and the magnetic flux density, B. So the formula of B is B equal to Phi over A. So because B is the amount of flux per unit area. So the unit for B is Tesla. So let's see this example. So find the flux density. So flux density is B in a magnetic field with the flux in 0.1 millisquare area. So this is your A. Okay, this is your A. So find B. So B equal to Phi over A. So your Phi is 800 micro over 0.1 meter square. So use your calculator, you will get, so 8 times 10 power of minus 3 Tesla. So this is the simple example. Magnetic circuit, one of the characteristics of line of magnetic flux is that each line forms a closed loop. So you refer to this diagram, or we call toroid. You can see the flux is form a closed loop. Okay, the complete closed loop followed by any group of magnetic flux line is referred to as a magnetic circuit. So magnetic circuits are normally found in motor, generator, transformer, and tape recorder. So these are a few applications using magnetic circuit. Air gaps, fringing, and laminated cores. So for magnetic circuit with air gaps, fringing occur, so causing a decrease in flux density. So when you have air gap, your flux density will decrease. So this is your air gap. So you have two magnetic material separated by air gap here. So fringing is actually this one. Okay, so you have non-uniform flux direction here. So this is your fringing. So normally in circuit analysis or magnetic circuit, so we neglect the fringing effect. Okay, and then the stacking factor is equal to effective area over physical area. So stacking factor we use when your material has laminated section. So where you laminate your material. Okay, so example 1, a laminated section of core has cross-sectional dimension of 0.03 meter by 0.05 meter. and then the stacking factor of 0.9. So what is the effective area? So stacking factor equal to effective area over physical area. Okay, so for A, okay, effective area equal to stacking factor times physical area. So given stacking factor is 0.9, okay, your area is 0.03 meter times 0.05 meter. Okay, you will get 1.35 times 10 power minus 3 meter square. So this is your effective area. And then for B, given your flux is 1.4 times 10 power minus 3 Weber, what is your flux density? So you just apply B equal to V over A. So A here is actually your effective area. Okay, so 1.4 times 10 minus 3 over your effective area 1.35 times 10 minus 3. So you will get 1.037 Tesla. So this is the example of stacking factor. Okay, and then this one, you have a car with cross-sectional dimension of 2.5 centimeter by 3 centimeter, and it has a air gap 0.1 millimeter gap. So if your density B of your iron is 0.86 Tesla, what is the approximate or corrected flux density in the gap? So here you have a magnetic circuit with an air gap. Okay, the first step is you have to find the phi. Okay, so phi equal to BA. So B, your flux density of iron is 0.86. Okay, times your A. Okay, A without a gap is 2.5 centimeter, and then you have to convert into meter. So time minus 2. So 3 times 10 minus 2. Okay, so this one you will get 0.645. Okay, so once you get the phi, you have to find a new area of your magnetic circuit with an air gap. So you have to find a new area with a gap. So this one you have to 2.5 cm plus, okay, so this one is in cm. Okay, and then 3.0 plus 0.1. Okay, so you have to convert to meter. So you will get 1.5 times 10 minus 2 meter times 3.01 times 10 minus negative 2 meter. So this is your new area with an air gap. Okay. And then once you get the new area with an air gap, so to get flux density with air gap, so phi over A with air gap. So your phi is here 0.645 over 7.555 minus -4. So your final answer of your flux density with the air gap is 0.854 Tesla. Okay. Next is series and parallel element. Magnetic circuits may have sections of different material. So, for example, the circuit in the following figures has section of cast iron, sheet steel, and air gap. So you have magnetic circuit here, but your magnetic circuit has different material. So you have laminated sheet steel type, and then you have cast iron type, and then you have one air gap. So this one two-dimensional diagram of your magnetic circuit. So you have laminated sheet steel, and then you have cast iron, and then air gap. So, and then this one is your source. Okay, you supply and current with number of turn n equal to 1000. So these are example of magnetic circuit with different materials. Okay, a circuit may also have element in parallel as shown in the following figure. So you have parallel. Okay, at its junction, the sum of fluxes entering is equal to sum of leaving fluxes. So this one is actually same with KCL, right? So KCL, so total of I in equal to total of I out. So same with magnetic circuit analysis, but here you have total of phi in equal to total of phi out. So if you refer at this node, okay, so at node, example node A here, so you can get the formula. So total of phi in, so phi1, okay, equal to phi2 plus phi3. Okay, the application of this formula is same with KCL. Okay, in addition, a circuit may also have element in parallel and series. So you have core and air gap. So as shown in following figures. So you have parallel here, but this one is, your gap is in series. So the analysis of magnetic circuit we will discuss later. Okay, magnetic circuit with DC excitation. So there are two basic problems to consider for analysis of magnetic circuit with DC excitation. So what it means, DC excitation is you give current supply to the magnetic material to produce magnetic field. So the first analysis where they give you the information of the flux, and then you have to determine the current required to produce it. And then the other analysis is the information of the current given, but you have to calculate the flux produced. So these are familiar analysis of magnetic circuit with DC excitation. Okay, MMF. So what is MMF? So MMF is magnetomotive force, where we call it the source of your magnetic flux. So this is your MMF, the source of your magnetic flux, where you have supply current and number of turn. Okay, the symbol of MMF is F, and then the unit of F is ampere turn. So you know that F equal to Ni. N is number of turn Okay, and then I is your supply current. Okay, and then this is the reluctance, or R, opposition to magnetic flux. So in electrical, reluctance is same with your resistor. Okay, so in magnetic circuit we use as reluctance, but in electrical we use it resistor. Okay, so flux in magnetic circuit also depends on the opposition that the circuit present to it. So term reluctance depend on dimension of the core and material. And then the unit of reluctance is ampere turn per Weber. Okay, so these are the formula of your reluctance. So reluctance equal to length of your material over mu permeability of your core material. So the permeability value is depending on your type of material used, and then the length is mean length of the path, and then the A is the cross-sectional area of your magnetic material. Okay, so this is the explanation on permeability. Okay, so permeability of free space or air gap, we use mu naught. So the value of mu naught is constant. Okay, and then mu r is depend on the material used for your magnetic core. So mu equal to mu naught times your mu r. Okay, ferromagnetic material have high permeability, hence low reluctance. So if you refer to this formula, so it will be proved by this statement. So non-magnetic material have low permeability. So once your permeability is low, so your R will be high. Okay, Ohm's law for magnetic material. So before this, we have learned Ohm's law for electric circuit. Okay, so same with magnetic circuit, we also use Ohm's law. Okay, the relationship between flux, MMF, and reluctance is, so flux equal to F over R. And the units of flux is Weber, right? So this relationship is similar to Ohm's law in electrical circuit. Okay, so in electrical circuit, source we use V, but in magnetic circuit we use as F or MMF. Okay, and then the current for electric circuit we use an I, but in magnetic circuit flux or Phi. And then for resistor in electrical circuit we use an ohm, but in magnetic circuit we use is as R or reluctance. So the concept is same between magnetic circuit analysis and electrical circuit analysis. Okay, so this is an example of simple circuit analysis or magnetic. Okay, so for this figure above, if the reluctance of magnetic circuit R is equal to 12 times 10 power of 4, so what is your flux in the circuit? Okay, so refer to the formula before. So F equal to Ni. So this is formula of your MMF. So you have the current 0.5 and your turn, number of turn is 300. So your number of turn is 300 times 0.5. So you will get 150 ampere turn. Okay, and then how to get the flux? So flux equal to F over R. Okay, so 150 over 12 times 10 power of 4, so equal to 12.5 with 10 power minus 4 Weber. So this one is relationship between MMF and flux. Okay, and then these are the last subtopic for part A, magnetic field intensity and magnetization curve. Okay, magnetic field strength or intensity, H, is a measure of the MMF per unit length of circuit. So before this we have learned flux, and then so flux density B, and then the last one magnetic field intensity, which is H. So these three parameters you have to differentiate the meaning and then the formula. So magnetic field intensity or strength is H equal to F over L. So H equal to F over L. So we know that F equal to Ni. Okay, so Ni over L. Okay, H is also known as magnetizing force. So you rearrange the equation here, so you will get Ni equal to HL. So this is how you get this formula, Ni equal to HL. So this formula, okay, so is very familiar to use in analyzing magnetic circuit. Okay, in electric circuit analogy, Ni product is an MMF source, while the HL product is an MMF drop. So Ni is your source, and then HL is your MMF drop. So this is Ampere circuit law. So Ni equal to HL is Ampere circuit law in magnetic circuit. And then the relationship between B and H. So the relationship between B and H, so B equal to mu H. So, and then where your mu is permeability of your core depending on the material you use. Okay. And then Bg is actually B at your gap. So you know that your gap is an air gap. So that's why you use mu naught. So mu naught is permeability of free space, where the value of mu naught is constant. Okay, so your flux density in the air gap is Bg equal to mu naught Hg. Okay, magnetization curve, also known as BH curve. So a ferromagnetic material, mu is not constant but varies with flux density, and there is no easy way to calculate it. So in order to get the value, you have to refer to BH curve. Okay, so this is your example of BH curve. So where it depends, the curve depends on your material of your core. So you have sheet steel, cast steel, and cast iron. And then y-axis is your flux density, and then your x-axis is your field intensity or H. So this is your BH curve. Okay, so how to read your BH curve? Okay, so you have, for example, B is equal to 1.4 Tesla for sheet steel. So what is your H? So you have to understand how to read the curve BH curve. So now, first you have to identify material used for your core. So here they use sheet steel. So this is your type of material. So just refer to the sheet steel curve. So this is your sheet steel curve. Okay. So your B is 1.4. So y-axis is your B. So 1.4 here. Okay. Okay. So how to get the value of H? So you just refer to this one. Okay. So you can use your ruler. So this is your value of H. So with B 1.4 Tesla for sheet steel, so from the BH curve you will get H equal to 1000 ampere turn per meter. Okay, so this is your answer. So you have to know how to read your BH curve, because all the analysis of magnetic circuit involve this BH curve reading. So that's all for part A. So any question on this topic, so you can discuss in WhatsApp group. So thank you.